Hey, hello. I will give a summary of recent LHC results. LHC is a heavy ion experiment at the LHC. And I will start with a short advertisement. We've published an analysis review paper related to Run 1 and Run 2 studies, about 200 pages. And we tried to wrap up all our knowledge and results on the QGP properties in heavy ion collisions, starting from macroscopic properties, going to interactions of partons with QGP medium via hard probes. We also touched hadronization effects and effects of initial state, and looked into various non-QGP details and other aspects of QCD and B. And I will try to follow this order and try to provide you the summary of latest LHC results. And let me start with the brief introduction on heavy ion collisions. In heavy ion collisions at the LHC, we have two contracted nuclei. They collide, and the medium which is created here is quickly thermalized at the time scale of about 1 Fermi over C. And then this hot and dense medium starts to expand. And at some point, it goes to the hadronic phase, and we finally find hadrons and other particles in our detector. And our goal is to try to understand what was going on in this hot and dense region by looking into the final state observables, by looking into soft and hard probes. And here we have a nice tool to do it, the LHC detector. I will go into details of all these detector subsystems. Let me just say that one of the main features of the LHC detector is that we have a broad momentum acceptance, allowing us to cover a wide range of probes from soft to hard probes. And here you can see a summary of all particle species we were able to measure as function of PT via decays and via PID. And this is another LHC feature, that we have a world-leading particle identification capabilities with time projection chambers and time of flight and colorimeters. And so here you can see a summary of all probes we managed to study. And I will start with soft probes, and in particular with macroscopic properties of the state we've produced in heavy ion collisions. And the most simplest probe is the particle multiplicity or particle density per unit of rapidity as a function of square root of n, as function of energy of the collision. And here you can clearly see that the trend we observe in heavy ion collisions is clearly different from what we have in proton-proton collisions. And this means that something is going on in heavy ion collisions, and we want to understand where this extra multiplicity comes from. And one of we can do the step further and check the energy density, initial energy density, which can be deduced from the multiplicity of the transverse energy. And what we measure in as function of multiplicity. And if you look into the highest multiplicity collisions, we see that the initial energy density which we produce is a factor 30 higher than the initial energy density which we may get from the latest QCD estimates. And that gives us a clue that what we are studying is indeed related to the quark-gluon plasma phase. And another indication that we crossed the phase boundary between hadronic phase and quark-gluon phase comes from the measurement of the effective photon temperature. If we measure the photon spectra in PT, then we find that the effective slope of this distribution, which is interpreted as effective photon temperature averaged over the whole collision history, is about 300 MeV, and this temperature is twice larger than the temperature which was predicted for the transition to the quark-gluon plasma phase in the latest QCD. And another observable that we can study is light particle spectra. And here you can see a comparison of different particle spectra in central collisions, which are shown with field markers, and with peripheral collisions shown with open markers. And you see that the spectra we observe are clearly different in peripheral and central events. So there is some suppression going on. And if we integrate, we can integrate this spectra and extract total particle yields at mid-rapidity and for central events. And what we get is the following picture. We managed to measure particle yields at mid-rapidity for a long list of particles, starting from pions down to helium-4 and anti-helium-4. And what is remarkable is that we are able to describe all these particle yields in a very simple statistical hadronization model. It basically assumes that all particles which we measure in the final state are produced at the phase boundary. And in this model, we have only a few parameters, like 2-3 parameters, needed to describe this particle spectra. And the remarkable feature is that this model describes these yields by 9 or 10 orders of magnitude. So this is a huge indication. And by the way, the temperature, which is one of the parameters in this model, appears to be about 156 MeV, which is again close to the temperature which is predicted for the transition to the QGP phase, to the critical temperature. And this means that most of the time, the medium which we study was above this temperature, and indeed what we study is was produced in the QGP. Charmonium provides us another tool to measure the temperature and to study the dense medium produced in heavy ion collisions. And charmonium was predicted the charmonium suppression was predicted to be one of the signatures of the QGP. And the idea was that in QGP, bound charmonium states are expected to melt. However, when we and indeed there was a suppression which was observed at Rick energies, shown with green dots as a function of multiplicity. However, when we go to higher energies, to LHC energies, we find that the suppression seems to be fading away. And the reason for that is that there might be some regeneration effects playing a role. The point is that in heavy ion collisions at the LHC, in central collisions, we produce up to 50 CC bar pairs, and there is a high probability that the J psi is produced simply by interaction of independent C and C bar quarks. And that provides that gives this rise of the array factor, which is a suppression factor, basically the ratio of spectra we see in central collisions to what we see in proton-proton collisions, properly normalized. We can get a further confirmation looking into this suppression pattern as function of PT. If you check this pattern, you see that for the suppression is much lower at low PT, and this is clearly explained by the fact that the largest multiplicity of CC bar quarks we expect at a low transverse momentum. Exciting charmonium states provided another interesting tool, basically a thermometer of QGP. The point is that we expect that loosely bound states are melt first at higher temperatures. And one of the most bound states is this upsilon 1s. It should stay, while upsilon 3s, for example, should melt first. And depending on how many, depending on the spectra we observe, we can judge on the temperature of the QGP. And initially, I must admit that the first observation of this suppression pattern was provided by CMS collaboration, where they observed the huge suppression of upsilon 3s state compared to upsilon 1s. And Alice complemented this picture by the studies of psi2s suppression, and here you can see psi2s suppression compared to gpsi, and one can see that indeed psi2s is suppressed much larger, and this is an indication that there is a this effect of melting going on. However, if you go look into the low PT region, we find that in addition to sequential suppression, we find some effects of regeneration, because at low PT there is some decrease of the suppression or increase of this ray factor. So this is interesting, and then can be used to deduce the temperature of the collision. We can also ask a question: what is going on in the hadronic phase? At some point, this hot medium, hot QGP medium, converts into hadron gas, and one of the questions we want to answer is: what is the duration of this phase, and what are the properties of the hadron gas we are studying? And resonances, short-lived resonances, provide us a nice tool to do it. I mean, ρ0, K star, lambda star, and other resonances. What we see is that if we go towards high multiplicities, the ratio of these short-lived resonances to their stable counterparts tends to decrease, and this indicates that this is explained in terms that at the hadronic phase, these resonances, they may decay, but in addition, there is another process, the rescattering of the decay products of these resonances with hadronic medium, and this results in this decreasing pattern. We can use this decreasing pattern to deduce the duration of the hadronic phase, and it appears that indeed, we can do this exercise, but for different particle species, we find somewhat different phase durations from 1 to 10 Fermi over C, depending on what we take. So this is the delicate question, and there's no clear answer yet, and we need further studies to understand it better. So here, I just want to provide a summary of various temperature scales we are measuring with different observables. Our hydrodynamic observables, which I'm going to speak next, provide us to study the whole evolution of the medium. Then the suppression of upsilon states gives us a hint that we are dealing with initial temperatures of about 600 MeV. Then photon spectrum gives us 300 MeV energy. And what we observe with the studies of the yields of particles, we get a chemical phase-out temperature of about 156 MeV. So all these pictures are consistent and providing us very nice and already quantitative results. We can do a step further and study anisotropic flow. The point is that in central or in non-central collisions, the spatial anisotropy converts into the anisotropy in the momentum space. And what we usually do, we study Fourier decomposition of the angular distributions of particles and study Fourier coefficients as function of centrality, transverse momentum, and the particles, and depending on particle species. And it appears that the behavior of these Vn coefficients, V2, V3, and V4, they are nicely described by hydrodynamic description. And what is even more remarkable is that one of the parameters, one of the key parameters, the ratio of shear viscosity to entropy, appears to be close to the ADS CFT limit. So we're dealing with really strongly coupled medium. And this is a surprise, because initially what we thought is that we produce a gas of loosely interacting partons, This is not the case at the LHC energies, but probably at some high energies, the quark-gluon plasma will behave like a loosely interacting gas. Not the case now. Now let's go to hard probes. We can use hard partons to probe the medium by studying the energy loss of the partons. What we usually do, we take jets, which are the remnants of those partons, and try to understand what is the energy those partons lost when traversing the medium. And usually we do it in terms of this suppression factor array as function of PT. And here again, I must admit that all experiments at the LHC, they contributed to this exercise. For example, here you can see results from Atlas at CMS at very high PT. And Alice contributed at relatively low PT up to about 50 GeV. And what we see is that there is a huge suppression of about factor 6 or 7 at a relatively low PT. And if we use various models which are predicting these energy loss of partons in the QGP medium, we find that indeed these models are able to reproduce this pattern, and moreover, now we're able to extract a quantitative information out of this spectrum, and we find that the energy loss per parton is about 8 GeV on average, and it is dominated by radiative emission. We are still working on various improvements, and one of the news is that now we're able to use machine learning techniques to extract this array factor down to even lower PT for jets, and also extend the radius of jets which we use. Now we went to 0.6, and I remind you that usually people use 0.4 for the jet studies, and that allowed us to roll out some of the models with this type of studies. Another hard probe which we study at the LHC is the charm and beauty hadrons, and here you can see nice summary of results on the suppression factor for Ds, for D mesons, and their V2 values as function of PT. From the experimental point of view, it is important to mention that now we're able to measure D meson PT down to 0 transverse moment, and this is an experimental achievement because it was a difficult exercise due to high background which we see at low PT. And from theoretical point of view, it was a challenge to describe both the suppression factor and the V2 values. The reason is, yeah, a few years ago, let's say, none of the models was able to describe both pictures. But now, after several years of work, theoretical models nicely reproduce the observed pattern, and we can now use these models to provide constraints on heavy quark transport coefficient, which is shown here. I will not go into details, but you see that the level of uncertainty is still high, but we are already on the way to describe it quantitatively. Another feature I wanted to mention is that if we compare the picture of suppression for prompt and non-prompt D mesons, we find that it is different, and non-prompt D mesons which come from decays of B meson decays, they are suppressed less than prompt D mesons, and this is expected from QCD. This is indication of mass-dependent radiative energy loss, that heavier quarks, they lose smaller amount of energy. You can see here that there is a large uncertainty on the theory predictions. For example, if you take this, there is a question or no? So, okay, if you take this low, if you take low PT region for this de Meson's case, for example, you see that there is a large uncertainty here, and one of the uncertainties in the theory predictions is coming from the fact that we have poorly known shadowing effects in the initial state. And one of the ways to constrain these shadowing effects comes from ultra-peripheral collisions. These collisions correspond to the case when two colliding nuclei pass by at impact parameters larger than the sum of nuclear radii, and in this case, hadronic interactions are suppressed, and we are left with electromagnetic processes. And the most remarkable process is when the photon emitted from one nucleus interacts with another nucleus, and the vector meson G psi is produced. And the feature is that according to leading order QED calculations, the cross section for this process is proportional to the squared gluon density in the target. So by looking into by measuring the cross section of J psi as function of energy, we can deduce the gluon density and gluon shadowing factors. And this is what was done. Here you can see a figure with the cross section of J psi photoproduction on LED as function of energy. And here you can see that it is the first time the J psi production is measured up to TeV scale corresponding to X values of about 10 to minus 5. And what we see is the huge suppression compared to the impulse approximation shown with blue, corresponding to the case when we neglect nuclear effects. And yes, if we build a ratio of this measurement to the impulse approximation, we can extract the gluon shadowing factor or nuclear suppression factor, as it is shown now as function of photon energy, but photon LED center of mass energy, but also here you can see a Bjorken X scale. Basically, what we see is that at 10 to minus 5, we are able to provide a gluon shadowing factor of the order of 0.5, and with rather good precision, and we are able to provide information on gluon shadowing in the region which was previously unconstrained. So this is good. I will probably skip this part, another example of ultra-peripheral collisions to save time, and go to the description of our I will present our results on the observables in small collision systems. Here you can see an event display from high multiplicity proton LED collisions. And one can wonder whether we produce QGP in this type of collisions. And this is not a terrible question to ask, because in spite of the, we basically produce a high energy density in a fixed and small volume, and in principle, one can expect a production of small QGP droplets. And that was expected a long time ago, even before the start of LHC era, and now we see a nice indication that this is what is going on. If we check the pattern of here you can see the yields of strange particles produced in small collision systems, and as function of multiplicity, and you find that the yields of strange particles relative to pions increase with multiplicity and reach the values which we have in heavy ion collisions. And the same trend we also observe for light nuclei relative to protons. So basically, we are reaching highest multiplicity ratios, which are comparable with lead-lead, and this is not the case for charmonium states and D zeros, where we see some discontinuity. But then one may ask a question whether we produce QGP, and indeed, it seems that light and strange quarks, they are thermalized at these short time scales in these short QGP droplets. This is not the case for charm. One may also wonder whether these effects can be explained by non-QGP effects, and there are some attempts to describe it using new developments in PIFIA, like color ropes, but I will not go into detail. Another confirmation of this QGP-like effect in small systems comes from the observation of the large elliptic flow values, V2, shown here for various particle species. And what we see is that as function of PT, we observe a clear anisotropic flow with the magnitude which is well described by hydrodynamics, where we take QGP equation of state from which we tuned based on lead-lead collisions. This is also confirmed by the pattern for pion, kaon, and protons, where we see an ordering which is also expected from hydrodynamic predictions. As I promised, I want to show a few examples where we do the studies beyond the quark-gluon plasma. We also have nice, interesting results. I just give a few examples. The first one on the studies of hypertriton. As I already mentioned, we produce light nuclei in heavy ion collisions, and they are copiously produced. In addition to light nuclei, we're able to produce hypernuclei. So far, we're able to study hypertriton. This is a state built from proton, neutron, and lambda hyperon. And this allows us to study the properties of this nucleus, and in particular to study the lifetime and consequently binding energy of this state. And what we found is that we measured the lifetime of this hyper nucleus with the best best precision, which is shown here, and we found that the lifetime is compatible with the lifetime of the free lambda hyperon, and that allowed us to reduce the binding energy. And it appears that the binding energy is very small, of about 130 keV. And this is very small, giving us a hint that what we are studying is a loosely bound molecule of deuteron and lambda. It is very interesting because the size of this molecule, if you take this binding energy, should be of the order of 5-10 femtometers. And the question is how this huge object is produced in lead-lead collisions, where we have a volume of the order of 10 femtometers. So very interesting and promising. We hope to do further studies. Another way to look into a hyperon nucleon interaction is using femtoscopy. Let me briefly explain what we do. We measure so-called correlation functions as function of relative as function of relative momentum between particles we want to study. For example, if we study proton Xi correlations, we take these two particles and measure their relative momentum and build correlation function. And it appears that the shape of this correlation function allows us to tell whether we are dealing with repulsive or attractive interaction, and we can also judge on the magnitude of the interaction and the strengths. And here you can see nice examples of proton Xi and proton omega. correlation functions which where one can see that there is a nice illustration that there is basically this is the first example where one can see attractive interaction between protons and Xi and proton and omega, and it is nicely described by various models. And this is an important study because proton hyperon interaction is needed for the equation of state at high density, and in particular for neutron stars, where we expect hyperons to be produced statistically. And the interaction with light hadrons is important to take into account. Finally, let me show this last example of studies beyond the QGP. Unfortunately, you don't see the title, but okay, this is a dead cone effect. Many of you know that this dead cone effect was first predicted 30 years ago by Doug Schitzer, Jose Trajan from my institute, and unfortunately, until recently, it was not observed. And Eris made the first attempt to observe it experimentally. What we do, we measure the angular distribution in jets where we have a charm hadron, dimeson, and consider angles between these charm hadrons and nearby particles, and measure this angle and compare this pattern with the pattern we observe for light jets, for inclusive jets, let's say. And we see a suppression as a function of inverse angle for charm jets divided by the inclusive jets. And this suppression pattern is nicely reproduced by models. I have to admit that this dead cone effect, the fact that the suppression of gluon radiation from heavy quarks at small angles is so the fact that gluon radiation from heavy quarks at small angles is suppressed was already included in all the Parton-Shao models like Pythia and Sherpa, but now we have the first direct confirmation of it. In the last part of my presentation, let me briefly describe our future plans. Yes. Here you can see LHC schedule, and we are somewhere here in Run 3. Run 4 starts at 2029, and then in 2035 we are going to install brand new detector. I will explain later why. And during this long shutdown, up to, until 2022, we upgraded our detector, and the main feature of the new detector is that now we are able to collect data in the continuous readout mode. Here you can see an event display of the data which we expect to come from the main tracking detector TPC. Basically, it is continuous, and this continuous mode will allow us to collect the huge integrated luminosity of about 30 inverse nanobarn. But even more remarkable is that we will be able to collect huge statistics of minimum bias events and study rare probes which we were not able to study in the triggered mode. We've started already collecting data in proton-proton collisions, and here you can see a pattern of our recorded luminosity as function of time. We collected about 28 inverse picobarn, and the data taken was at about 50 kilohertz, corresponding to rather small mu values of about 0.02. That should be compared to typical values of about 50 in Atlas and CMS. So basically, we are trying to measure proton-proton collisions in a clean environment. And the idea is that we store all the data on tape or on disk, and then we have several months to analyze it and to perform software-based trigger selection, basically selecting our rare probes which we want to study, and then we store it permanently on disk. And here you can see nice examples of our performance for TPC PID and for TOF PID. A nice example of our charm measurements. Now, basically, we already have about factor 100 more statistics for charm measurements. And a nice first signal of anti-helium-4. And this is remarkable because you can imagine how difficult it is to produce this light nucleus in proton-proton collisions. We also got a chance to taste the smell of heavy ions last year, and here you can see a nice event display from the first lead collisions in Run 3. And this year, in October, we were able to continue and this data taking and start full production. And here you can see our pattern of integrated luminosity as function of time. And at the end, we were able to collect about 1.5 inverse nanobar of data corresponding to about 12 billion lead collisions. This is already factor 40 or larger minimum bias sample compared to Run 1 and Run 2 harvest. So now we are trying to reconstruct this data, and this is another challenge. Now, a few words on our future upgrades. In Run 4, which is going to start at 2029, we are going to install the new inner tracking system and the new to measure photons at forward direction. And finally, in 2035, in Run 5, as I said, we want to install the new detector based mainly on silicon technologies, and I invite you to follow these links and to check the details. Let me go to my summary. So I showed that we got a wealth of physics results from Run 1 and Run 2, and we switched from qualitative statements to quantitative measurements. And now we perform successful upgrade of our detector and switch to continuous readout that allows us to get a huge increase in statistics. We already got factor 40 increase in minimum bias statistics for lead. And the plan is to analyze this data. And then let me just invite you to join us in this journey through QCD with us, looking into this review paper. Thank you.
Thank you very much for the nice presentation. Please, questions from Zoom first, as usual. Maybe questions from the audience.
Could you explain in more detail what does the energy density means? At which stage it is measured? Just after collisions, at the stage of plasma, at the beginning stage of plasma, or at the end stage of plasma, or at the stage of quark-gluon plasma? What is initial point?
You probably refer to the first plot which I showed, deduced from multiplicity measurements and transverse energy measurements. This one. I'm not an expert in this plot, I must admit, but what I remember is that we are dealing with initial energy density corresponding to the thermalized, after this one Fermi over C, where we got a thermalized medium.
And how do you extract it from data?
Well, we have some theoretical predictions. The most simple one, I guess, is Bjorken picture of the collisions where we have some relation of
It is in the
energy.
framework of the Bjorken model.
Probably more advanced, but here I'm not an expert.
Thank you.
Thank you. More questions and comments, please. Maybe first. Так, Роман. Thank you. Could you please tell what are, well, if there are any bounds on production of anti-nuclei, namely anti-deuterium and possibly anti-helium, in any known experiment, in fact, not necessarily at least.
Any bounds on what?
On production of anti-nuclei, anti-deuterium or anti-helium.
So we did produce anti-deuterium and anti-helium, and even anti.
Yes, but any known limits or
Limits on what?
on production, cross section or whatever.
Well, we measured the yields, and
Or maybe I missed it. Sorry.
Next. So here you can see the range of particle species we measured, and here you can see deuterium, helium-3, helium-4, and anti-helium.
Okay, thank you.
So
maybe I
all of
was
them,
late.
yes.
Thank you. Sorry.
Okay, thank you.
So-
Maybe only even helium.
Only short comment, very short question, because we have to come to lunch.
One quick question. Is cone suppression effect specific for QCD? Because we should observe the same in pure QED processes.
I think yes. This is a.
So this is not related to kinematics only.
No, if I understand correctly, this is there are similar effects in QED in.
Yes, for final state radiation of muons, for example.
Yes, yes.
So this is not QCD specific.
Yes, but the first time it is observed and clearly measured in QCD.
Let me thank the speaker again, and